Welcome to Haskell Live. In this episode, we're going to take a look at the code we wrote last episode and make a few changes. There are some bugs we need to fix, there's some smells we need to alleviate, and there's some code that we need to refactor to be a bit more clear as to its intent. We might actually get some performance improvements, but mostly we just want our code to be a bit more clear. To get started, let me explain really briefly how my environment is set up, and there will be more information about this, including a bunch of links, in the episode notes at haskelllive.com. So first of all, I've got tmux here, which is a screen-like thing that is more awesome than screen, and it's got a split pane, or two split panes here, with Vim at the top and guard at the bottom. Vim is of course Vim, and guard is a Ruby program that watches for file system events and then lets you do some arbitrary thing. In this case, my arbitrary thing is running run ghc on the file that changed. So since our main is running tests, any tests we might have, right now we have none, but any tests we might have will get run, and it'll at least compile or not compile and show us what happened. So we can see that in action there at the bottom. I added in a couple of echoes just so that we can see it working. There we go. And then finally I have a separate window running ghci where we've got our chess module loaded. So in Vim, I now have ghc mod, which gives me hlint and hcheck warnings as those little double arrows at the far left of my Vim screen. For instance, this warning is telling me that quick check is redundant because I'm not checking anything yet. So let's comment it out until we need quick check, just so it'll shut up about that. Initial board string doesn't have a type signature, so we will add one. And read piece has a non-exhaustive pattern match, and we'll come back to that. That's a bit more serious and involved because that's an actual bug that we need to fix. Tests needs a type signature, and this one here is defaulting to an integer, but it's not unambiguous. So we're going to give the inferer a bit of a hint as to what we mean by giving the one its own type signature. Prop empty needs a type signature. Run test has a redundant do because right now we're just calling return until we turn these tests and quick checks on. We'll get rid of that. Then we'll give it a type signature. And that is all of our warnings except for this non-exhaustive pattern match. The non-exhaustive pattern match happens because while my function has the domain of all characters, I'm only matching this subset of them. What I really need to do is make sure that my read piece function is not a partial function from some subset of characters, but it is in fact a total function from the entire set of characters, the entire domain of characters. So, since there are a bunch of characters that are not valid pieces, this function will only sometimes return a piece, or it will be a maybe piece, which means each of these constructors need a just constructor. So those are now just that piece, and anything we don't know about is a nothing. Now that that compiles, we've got our next error, which is that the type signature of read piece is changed, and that affects read square, which calls read piece. Now, read square is from a character to a square, but if we recall, a square is in fact a maybe piece, as you can see on line 28. So read square of something it doesn't know, or something that read piece doesn't know, could be nothing, and read square of a character that read piece knows could be just that piece. So we can actually just say that read piece is the same thing, or rather read square is the same thing as read piece. And that will get us compiling again and get read board working in the way we want it to. For instance, read that, read board, initial board string, and we can see that it does return the correct board. And when I say correct board, I of course mean the incorrect board with all black pieces at the bottom, which I didn't notice last time. So let's go ahead and fix that as well. There we go. I hope I didn't drive you guys too crazy with that one. Now let's try that again. Ah, white pieces. Just like science intended. Okay. So before we revisit this decision to have show square, or rather have read square, accept invalid characters as empty squares, let's first talk about the redundancy in read piece. Now, earlier I said, rather ironically, that I'm okay with redundancy as long as it leads to the characteristic of a function being obviously correct. And what I mean by obviously correct is that it's obvious how the function maps each input in its domain. And it's obvious that each mapping is correct. And it's ironic because, of course, many of the mappings of a partial function are by definition incorrect because they're not mapped. So now that it's a total function from character to piece, we can inspect it for obvious correctness. Each of these characters that it knows about is mapped to just the piece that it corresponds to, and any other thing is mapped to nothing. So that's, I think, obviously correct. It's pretty clear that each mapping is correct. But there's a lot of redundancy. There's a lot of calls to this piece constructor. There's a lot of calls to this just constructor. And there's also redundancy in the relationship between uppercase characters and white pieces and lowercase characters and black pieces. So what can we do to reduce that redundancy or to make this code more dry? For starters, we can have a lookup. We can have a list of two tuples that Haskell calls an association list that it uses sort of like a dictionary. We'll call this type list. And its type is a list of tuples from character with the first as character and the second as piece. So we start with a P, which is a pawn. And then we keep going. Pawn, knight, bishop, rook, queen, king. Okay. Ah, and of course it's not a character in a piece, it's just a character in a piece type, because piece color can be determined based on whether it's uppercase or not. So now that we have a list of characters and the type of piece that they refer to, we can rewrite read piece in those terms. Read piece will now take a character, and the first thing it will do, it will look up the character, or in fact, the to lower version of the character, because all of our characters in the map or in the lookup table are lowercase. So it'll look up the to lowercase version of the character from the type list. And of course, we'll add to lower by importing data.char. Now, what does that give us? Nothing yet, because what we're actually getting back is a piece type, and we need to turn that into a piece. So we'll need a constructor that takes a type and returns a piece. And we determine which color that piece will be by checking if the character is uppercase, then it's white, else it's black. Now, oops. What does this error tell us? It tells us that we're returning a piece and it's expected to be a maybe piece. How are we going to solve that? Well, this returns a maybe piece, and we want to apply this constructor, this piece type, this piece function, or this partially applied piece constructor that takes a type, only if we get a piece and not nothing. And to do that, we use fmap, where fmap of some function onto nothing is nothing, and fmap of some function onto just a is just that function applied to a. Or in type notation, it's a function from a to b, and a functor of a, where maybe is a functor, returns a functor of b. And as I said, the behavior of fmap for maybe is that nothing stays nothing, and that just something gets the function applied inside of it. Let's also go ahead and use some explaining variables for these. This is lookup type, right? It gets the type of the piece from its character. Compiles. And this is a function that takes a piece and makes, or takes a type and makes a piece, right? Okay, so now we know that our read piece maps the function make piece into the functor, the maybe, returned by lookup type. So if it's a nothing, it stays a nothing, and if it's maybe a piece type, then it becomes maybe a piece, and what we want is maybe a piece. So let's take a look at that in GHCI, make sure it works. Read piece A is nothing. Read piece pawn is just the black pawn. Read piece white pawn is just the white pawn. All right, that looks good. And this bracket is redundant. Thank you. Thank you so much, HLint. All right, that looks good. Now that we've refactored read piece, we have a decision to make about read square. Oops. Right now, we are being accepting of input, which is to say that no matter what character we read, we will always return a square. If the character represents a piece, we'll return just a piece. And if the character does not represent a piece, we will return nothing. And that works in the sense of if the board is valid, we will get a valid, if the board string, the string representing the board is valid, we will get back a board that is valid. But it doesn't work in the sense that if the board that we are reading as a string contains characters that shouldn't be in there, contains invalid characters, we'll still get back a board. And what we need to do is we need to separate the semantics of a valid piece from an occupied square. What I mean to say is if we try to read a character that does not represent either an empty square or an occupied square, then we should get back some sort of error. And one way to encapsulate errors in Haskell is with the maybe monad. So what we're going to do is we're going to change read square to maybe be a square. What that means is maybe it'll be empty, maybe it'll be occupied, or maybe it won't be a square at all. Maybe it'll be nothing because we tried to read the character and it completely failed. So one trivial way that we can accomplish this task is, since right now we're accepting of input and we know that read piece always returns a piece, or always returns a square, we just wrap that in the just constructor. What that means now is that read square is a function from character to maybe square, and read board is now no longer going to work properly because we are taking a function that expects a square and giving it a maybe square with read square. So one thing we can do, since we know that read square is always just a square, is we can get it out of there, right? We can get it out of there. Maybe we can get it out of there. But I actually don't like that, even if we could get that to work. And the reason I don't like that is I want to retain the concept of the inability to parse a character all the way up so that our read board maybe returns a board, and if the string it's trying to read contains invalid characters, it returns nothing. So let's comment this out so that we can get back to compiling. And let's decide what we want to do with read square. We want to handle the case first of reading an empty square, which is just nothing. That sounds odd, but just satisfies our maybe requirement, and nothing is the type of square that it is. It's an empty square. Now, what are we going to do about read square for some character? C. Well, again, we're going to use fmap. And we're going to use fmap so that if we get back a piece, if we get back a maybe piece, we want a maybe square. And we get a maybe square from a maybe piece using the just constructor. So we're going to map just onto read square C. Read piece C. And what that means is if read piece C returns nothing, read square C will return not just nothing, but in fact nothing at all. So let's see if that works. What does read square of the empty square return? Just the empty square. What does read square of a piece return? Returns a piece. And that just is a little bit confusing because we haven't added any new types to represent empty versus nothing and occupied versus just. So what this actually says is it's just a square occupied by a piece. Whereas read square with a dot is just a square that's empty. And read square some other character that's not a piece is nothing at all. Now we can come back to read board and figure out how we want to handle it. Well, what we really want is if there are any nothings in this map of read square, that we get back nothing. And if there are any nothings in the rows that we've mapped, we get back nothing. So we'll use map m. Now let's take a look at that. Map m, and let's write this up here, takes a function from something of type A to something of type B wrapped in a monad m, and then it takes a list of A's and it returns a list of B's wrapped in the same monad m. So let's look at how that actually works in GHCI. So if we map m read square across a string containing all characters, we get just the array of squares. But if one of those is not a square, we get nothing. And likewise, if we read rows, we'll get back a list of rows, where those rows will either be arrays, or it will either be lists of squares or nothing. And if any of those rows are nothing, we get back nothing. But so now that we know how to write our read board, let's look at refactoring it. And we'll refactor it using the laws of composition, some of the most basic laws in Haskell. We will start by inlining map_m, or this read row. And then we will recall for ourselves the type of function composition is that it takes a function from b's to c's and a function from a's to b's and an a and returns a c. Or in this case, what's the type of map of f? Sorry, read square. Well, it takes a lists of characters and returns a list of maybe squares. So our b's to c's is map, and our a's to b's is also map. So what we actually have is the type of map composed with map of read square is the same thing. So composing map with itself allows us to map into a list of lists. And composing map_m with itself allows us to read into a list of monads and then lift that resulting list out into the original monad. All right, now let's take a look at this code. We can do the same thing here. Map.map show square. Sudo do the same thing here. And let's make one more change. Instead of returning nothing for the error case of read square, let's return an error string that describes why it failed to read the square. That means instead of read square being a function from a character to maybe a square, it'll be a function from a character to either a square, either a string representing the error, or a square. And we will get there through the cunning use of control.error.utils note. And what note does, let's get this compiling again so I can show you more easily. What note does is it turns a maybe into an either by providing the note that you want to attach in the case that the maybe is nothing. So our read square, when it turns into an either, is just note some error message applied to that nothing we returned. Oops, that would be here. Applied to that nothing we return from f mapping just onto read piece, where error message is something useful like error reading square, show of character. So the character is not a valid square. And these two justs are instances of return that are specific to maybe. So we can replace them with return, where return will lift it into any monad, and in this case, it'll lift it into the either monad by lifting it by using the right constructor. And readBoard now has the wrong type signature, so we will regenerate it. And Haskell mode thinks it's a list of squares, but we know that it's really a board. So readBoard now takes a string that represents the board and either returns an error that tells us why it couldn't parse the board, or it returns the board that it parsed. So let's try that out. Reading our initial board string gives us an error that says the empty space character is not a valid square. Oh, and by the way, turns out I don't need those. That's what you get for doing it live. Okay. Because these, as one of my watchers so kindly pointed out, would be better off as dots. Okay. Let's read that again. Now, with a valid board string, valid in the sense of all of the characters in it are either representations of or some sort of representation of a square, we get back the board inside the right constructor. And if we read board some board string containing a bunch of crap, we'll get back an error saying that the first invalid character it found, in this case A, is not a valid square. And I will leave refactoring of showpiece to use this type list, possibly inverted, as an exercise for my wonderful watchers, and I would love for a pull request. That will just about end episode 2. Thank you all for watching, and please tune in again next time. If you have questions, come find the link to the GitHub issues page at haskelllive.com, and please let me know. Or if you think I'm doing something stupid that Haskell lint didn't catch, let me know that too. All right, thanks so much for watching.